Hello, everyone, and welcome to our Senior Design Conference presentation on the Metal 3D Printer Hybridization Project. I am Vincent Massoni.
I'm Christian Avery.
I'm Taylor Gergen.
I'm Jack Kester.
Let us begin with a quick intro to our sponsor. We're sponsored by the SD Space Grant Consortium. Previously, when this system was being designed, it was sponsored by the U.S. Air Force. And when it was converted into a master's thesis, it was sponsored by the Department of Defense. Here's a brief look at the state of the art. As you can see here, we have the traditional metal 3D printing technology, which is powder bed fusion, which uses a laser to sinter powdered metal together. And then down here, this is the type of 3D additive manufacturing that we're going to be using, which is wire arc additive manufacturing. Now, a little bit about additive manufacturing. It's a cost-efficient solution, and it's environmentally friendly because you do not waste as much material just on machining it away. And it allows you to have more complex geometries and fewer assemblies. And a little bit about the 3D metal printing industry is that it's valued at $3.15 billion, and it's expected to grow 22.9% in the next 7 years. The only problem with this is there are remarkably few low-end models. The current price ranges are from $100,000 to $200,000. And here's our metal printer. As you can see here, we have the gas metal arc welder and the end mill, making this a hybrid system. It's designed to be a cost-effective solution, efficient, precise, and scalable. And we hope to improve on the already existing design.
So now we're going to get into our project goals for this year. So our overarching project goal statement is to improve the already existing 3D metal printer by incorporating the milling process and making higher quality prints. And then by the end of next semester, we are planning on printing a South Dakota State University logo. So here's a couple of our mandatory goals, the goals that we promise to have done by the end of next year. And we'll get into detail more on these later, but just to give you an overview of what they are. We're planning on having a higher level of automation with our metal printing. We're going to incorporate a retractable welding apparatus. We are going to have the addition of an emergency stop. We are going to develop an instructional workflow. We are going to create standardized 3D metal printer-specific G-code. And then the end mill is currently on the system we are going to have operating. And then we also going to convert our wire feeding operations from a DC motor to a stepper motor.
So next, we're going to go over a couple things that we did in our design phase in order to reach some of these goals. The very first thing we had to look at is what kind of controller we wanted to control this system. We had to decide between keeping the ramps 1.4, which is currently in the system, and changing it between two options. The two options we picked out were both the same controller in a sense. They're Duet 3D, 3D printing specific controllers. The only difference is one is made genuinely by Duet, and the other one's kind of a cheap knockoff that we could get overseas. The big difference between these two are that the genuine is about $250, while the knockoff is about $15. Some of the main criteria we looked at are price, the milling capabilities of these controllers, or how easily they can be turned into a mill or router, the user community online, how active they are, the reliability, kind of like what the reviews are saying online, the initial work that it'll take to get this controller going, and the ease of use afterwards. The ramps 1.4 actually won in a lot of these categories, a major one being like price and initial work. This is due to it being in the machine already. We don't have to buy it, it's already in there. But we did make sure to look at the ramps 1.4 and its capabilities to make sure that it could do everything that we needed in order to reach all of our goals. The ramps 1.4 is an Arduino Mega Shield. It's made specifically for 3D printing capabilities and similar uses. So it's got stepper motor drivers specifically for movement, and then a couple also for extruders. You can put an LCD display. It's also got a couple extra outputs that we won't be using them either specifically for that use. We can use them for something else. Something like that would be our welder trigger. So right now, the machine that we have The movement of it is controlled by stepper motors, which is controlled by the controller. However, there is the welder that is controlled manually by a switch. This introduces a lot of human error into the printing process. So we decided to take a fan output on the controller and hook that up to a 12-volt relay, and that's going to control that welding trigger. That takes a lot of the human error out, and we can actually then have G-code specific demands that turn on and off the welder when we would like it to. The next thing we had to look at is implementing the mill into our processes. The mill is a AC motor spindle. It's going to be controlled by a VFD or variable frequency drive that's powered by 220-volt AC from the wall. We decided to go with a PWM output on the board, which already comes with a PWM output. This gives us a resolution of about 8-bit, so we can decide on different speeds for the spindle.
Looking forward, because we have to run the mill with our system, we want to make sure that we can safely do it without damaging anything on our system. So through visual inspection, we were able to find our points of failure are going to be the bolts connecting the mill to our gantry system. There are going to be 2 points at which we fail here. First, the bolt head could be sheared off, or the threads could shear off themselves. So we did do a calculation which would determine how much material we could take off each run of the mill when the bolt fail. So we used a factor safety of 5. And we also assumed worst case scenario for each time, assuming that the mill face will actually be the entire diameter of the mill. We're currently using a 3/8 mill bit. So before the bolt head should fail, we expect that we could do 1.92 inches and 33 thousandths of an inch before the mill threads would fail. The shop standard is already set at 30 thousandths inches per mill thread, so we're going to stick with that for our milling. We also have the retractable welding apparatus, best picture here. As you can see, it is simply a platform which we are looking to raise and lower when we start our milling process. We have to do this because in that photo there, you can see that the welder head is much lower than our mill head, and we do not want to plunge in the material once we commence our milling operations. We are looking to add this to our injector. Our injector is going to be injecting code for us instead of us manually having to implement it. This will inject before the milling operations commence, and then once the milling operations have finished, it will lower down the apparatus. Next, we have the conversion of our wire feeding operations. Currently, the wire is being fed by a DC motor. This DC motor is controlled by our Hobart welder and the manual operation of the welding trigger. Once we convert our operation of the welding trigger to be automated, we will use an automated feed system. To do this, we must switch from a DC motor to a stepper motor, as the Cura slicer, which we use to slice apart our CAD models, only gives feed rates for a stepper motor, so we do have to convert those. Next, we have our emergency stop. Currently, if something goes wrong during our print, we do switch off the power strip, but this isn't obvious for first-time users, so we are looking to put in an emergency stop above the power switch to stop things like the end mill, welding trigger, and the stepper motors. We do have some items that will not be stopped by the emergency stop, like the cooling pump. The cooling pump is used to cool our end mill, and if we were to stop operations after it has been milling and heating up, we don't want our parts to be damaged, so we want the cooling pump to be powered by a separate system other than this power strip. Here we have some photos of our test prints. It is the first layer, second layer, and a partial of the third layer. In the first layer there, you can see that there are some gaps between welds. This is because we had to restart our process a few times, so the operator didn't start the welder in time, or they stopped it too early. In the corners there of the infill, you can see either no material or too much material, because the current slicer we are using is going with a variable feed rate, while we are using a DC motor, which is constant feed rate. So that should be solved once we put in a stepper motor for our feed motor. The second layer printed quite well, but then when we got to our third layer, you can either see there is some deformation of material. This is caused by all the heat that is going to the material when you are doing a welding process. This caused us to stop printing, as the material here was much closer to the weld tip as the material here. So this was causing backburn and was welding our welder tip shut, so it was damaging our equipment. solve this issue, we are going to look to solve it with our injector to inject pauses to our prints so that we can wait for heat dissipation before we continue to print. And we're hoping that this will stop any warpage. We are going to look into a few other ways we can dissipate heat faster, but this is our solution for now. All right, now speaking of the standardization of our G code, a lot of the specifics are going to be where we put dwells and where we put various other commands, which control the welding apparatus. And so I'll walk you through a little bit of the process for us. So we start off with a CAD model. And from that CAD model, we import it into our slicer, which is Cura. And from there, Cura spits out our G code. And from there, we're creating an injection tool to inject specific commands at certain points so that we can have things such as dwells within our code automatically created. From there, we move it to our control software, which sends it to our printer, and we get a final print. Now, here's a little look at our workflow. First off, we start off with slicing the CAD model and all that goes along with it. And then we move into our safety checklist to ensure we're being safe while operating this machine. Then we load in a new print bed plate so that no warpage from prior prints messes up the current print. Then we prepare our welder for operation and begin printing. We then move into our shutdown sequence. We remove the print bed, we clean up, and finally, we have our final print.
Now looking into our budget for this semester, it's pretty low in terms of it's only a couple $100. Currently, we've already bought the welding wire and the printing plates as we needed those for testing. But a couple of other things that we will be needing is some extra wiring, our water bucket to put our water pump in when we get the mill up and running, and then our e-stop components. So then also look at our Gantt chart. Everything in blue is everything we've already done this semester. A lot of it was research into the components in our machine, and then some initial testing also to see how our machine really worked. Moving forward to next semester, everything in this is how we're going to accomplish the rest of all the tasks we've already kind of shared with you. So we're going to hopefully have our automated welding trigger completed by the end of January. We are going to have our retractable welding apparatus completed by the end of February. And then we are going to start our final print by the beginning of March, and then have everything wrapped up by the Senior Design Conference in April. So we thank you all for coming out today. And if you would like, please fill out the survey. Again, we are the Metal Printer Hybridization Group. And if you have any questions, feel free to ask those now.
Yeah, so when you guys are saying you get done with the print, do you basically just have to cut your part off then, or?
Right now, yeah, because the mill doesn't work on there quite yet. Last year, Ryan, who was the master's thesis running this project, he would just mill kind of a circle around it till it came all the way off or cut it off.
Oh, okay.
But we're hoping that our mill, once up and functional, can actually just cut out the piece
So
itself.
then you'll just have your initial piece of it tested as the part split.
Yep. Yeah.
You guys plan on doing angles?
Jeff,
Are you saying welding at angles?
Like,
Overhang. So we did find a piece that Ryan did print where it was, he built up 3 sides of the box and then he started printing over the box. He was able to successfully do that. We cannot find the CAD model which he used for the way that he did that. Currently, our objective is simply to do a complex shape, which is just the SDSU mechanical engineering. But with further research is to go into it, we can hope that they might get some more overhangs done. We can do simple overhangs right now because we just be printing on basically the shoulder of the last weld bead in the prior layer, but we can't do too complex overhangs. We could look into that. There was an issue with the welder early on as they were getting what we call snowflake welds because there was a grounding issue and it was solved by a piece of electrical tape. So right now,
The way the weld is secured, the welding tip is secured in there is just wrapped in electrical tape, so it's not transmitting current to any other part of the machine. So if we were to have a rotating system, it might cause more errors with the same issue of snowflake welds. We could look into it, but
We're mostly looking at simple extrusions. Overhangs kind of out of the scope of this year at least, but yeah, it's kind of hard working with molten metal. But yeah, that is something we saw kind of remnants of, but haven't been able to find out how.
What type of like final parts do you get off of, like work like? I guess what kind of parts are you hoping to be able to make on it that will be able to be used?
That would probably be mostly what you'd see machined. Being the mill would be a big part of this, but machining has where you take one piece of stock that you end up not using a lot of. You would mainly just deposit material where you would need it, and then you would have a machined part. Probably not super complex geometries, but something you'd see from a.
Do you have any like goal of like what type of geometry you're hoping to be able to successfully do?
We have right now a final print that we thought it'll be a SDSU logo that's both. I mean, you can kind of see the welds on it, and then it's machined on the top. That kind of, in our mind, is the final capabilities that we want the machine to be able to do by April. Anything extra is just kind of icing on the cake.
And then I saw in the detail that you're doing 1.75 millimeter layer heights. Is there any like reason that we chose that height, or just that's kind of what we're?
Yeah, there was some testing beforehand that we did on handwritten G code, and then when we use the slicer, we have it as a custom printer, and that's why we chose that specific layer height.
So to go back on to the parts. Solid metal.
so we may not have a fully solid piece, but there are ways that we can make it a denser piece. So by decreasing the distance between the lines, I believe right now we have the line width set to 7 millimeters.
Something like that, yeah.
7 millimeters. But if we were to shrink that down, we would have welds closer together. They would butt up against each other, and this could cause more issues. But it would also increase the layer height, and then it would fill in some of those gaps.
Good, why not actually overlap the worlds?
So we are currently using a pattern generated by our Cura slicer. If you could go back to our test prints, you can see that the infill is done with a zigzag pattern. Out of all the patterns that give you an option to choose, we thought that this one was best because there are the least gaps between material. A few others were cross hatching, where it's just a set of lines vertical, set of lines horizontal. This one did have that center square with the without material, so this is what we are set on for our first run at least. But if we do find that the pattern works better for us in the future, we'll switch to it.
This I see that is good. Well,
We also are considering like machining after each weld, or at least a couple. This would then kind of fill in those blank spots. It's kind of like you can cheat being a good welder with an angle grinder. You just would cheat it with a mill.
It's like, you have an idea of what the scale is, how big is that rectangle?
This is a 6 by 2 inch.
Yeah.
The speeds and feeds we're mainly running off of are something that Ryan kind of found out in his master's thesis. His was a material science master's thesis, more specifically. He was using this machine and obviously perfected it, or got as close as possible. And he tested the material off of it to make sure that this is a viable option for additive manufacturing. So we kind of decided to not change anything that he did just because he had tested that material out in terms of how fast he was going, and their height and such.
How much use of angle would you be able to make, since I guess you have some like rounded edges on the corners?
That's a good question. These zigzag models actually have, it's kind of hard to see. And again, like this is a DC motor, so a constant spindle. It does not change for going around corners, which we're hoping to mitigate a little bit within stepper. But this zigzag will go up and then kind of straight up like that. So you're seeing it, 20-degree angles sometimes. They're pretty small. But that's kind of where you can see that big floppy overhang. And the outside that straight 90-degree, you can even see just a little bit of extra material being deposited there that we were hoping to get away from with the stepper motor. Absolutely. Yeah, the mills, we're hoping going to be kind of the problem solver to a lot of these issues we see come up.
So that's kind of my question. The mill is actually part of the shaping process.
Mm-hmm.
I guess I was originally thinking that the mill was just to kind of level off the well, and level it off. It's actually part of the shape.
Yep. Yeah. Yeah, we're I mean that'll be both the desired finish we'll get out of the mill and the final precision tolerances and everything.
I think we are.
Sorry.